Blog Talk Radio.
Hello and welcome to a September 4, 2008 segment from the Kentucky Water Fuel Museum. Today we have a very special guest with us, Professor of Cosmetology Wasley Krogdahl. And Mr. Krogdahl, are you with us?
Yes, I am.
Welcome to the program.
Thank you.
Now, you have quite a distinguished standing as a Professor Emeritus of Physics, Astronomy, and Mathematics. And I understand that that's quite unusual to have such vast experience in instruction of science subjects in a university.
Well, it used to be, but today it is not as unusual as it was. In order to be an astronomer, you have to know mathematics, and in order to be an astrophysicist, you have to know physics. So there are a great many, meaning a few thousand at least, scientists in the world who know all three to some degree and use their knowledge to study the universe.
Very good. And so this study is generally known as cosmology?
Yes, cosmology studies the universe as a whole, the entire universe as a unit, just the way you'd study some part of it like the Earth or the Sun or the solar system or the Milky Way, except this includes all of those, everything you can see in the universe.
Okay. And this requires you to become fairly well acquainted with hydrogen because hydrogen ends up being the main component that the universe is made of, huh?
Yes, the universe presumably started as hydrogen, pure hydrogen, and a portion of it was converted into helium during what is called the Big Bang. And in the stars, even now, as in the sun, hydrogen is being converted into helium, and energy from that reaction is released as heat and light, which keep the Earth warmed and habitable.
Very good. So this is a sort of a perpetual motion type machine, this sun of ours. Is that right?
Well, it isn't perpetual. The sun will eventually die, just as every other star will die, because there's a limit to how much energy it can create out of the hydrogen that it has. So stars have lifetimes, which range from what astronomers would regard as short, meaning a few million years, to very long, meaning a number of billion years, depending upon their size.
Now, what about the possibility of reproducing a reaction similar to what the sun does to continuously produce the heat and light that we benefit from? Is there any possibility, or has anyone attempted to do this on a small scale?
Well, in an atom smasher, you can create the same reactions on a very small scale, and it hasn't been done on in a sustained way. It has been done one reaction at a time, and that's pretty small potatoes.
Yeah. And now, what about the... there's so many things we can talk about. You and I have had a couple of discussions, and some very interesting things have come up. And I think the general public is totally unaware of these things. I mean, even one of the basic statistics of the percentage of hydrogen that comprises the universe, the fact that it's 90-some%, perhaps 97%.
Yes, the assumption is that it was originally all pure hydrogen, but that in the very early state of the universe, the matter became very hot, very dense, and this resulted in nuclear reactions which produced helium from hydrogen in much the same way that the sun is producing helium from its hydrogen. So that created a lot of initial energy.
Now, when we talk about the vacuum of space, people, I guess, think that there's nothing there, or it's empty, or whatever. But in actuality, there is an atom or a molecule of hydrogen per cubic yard of space or something. Is that correct?
Oh, yes. What we call outer space is not totally empty, although it's probably more empty than the best vacuum that can be created on Earth. As you quoted, about one hydrogen atom per cubic yard is all there is, and that's pretty empty, all right. But it's not completely empty.
Yeah, isn't that fascinating, though?
In between galaxies, there is very, very little, even less than that. In our own galaxy, which is the Milky Way, between the stars, there are some volumes which include a much denser cloud of hydrogen and many molecules that have been the result of combination with hydrogen and other atoms. But between our galaxy and other galaxies, the space is much more nearly a perfect vacuum.
Very interesting. Now, you mentioned previously that hydrogen actually reaches our planet from the sun.
Oh, yes. There's something called the solar wind, and it is it is solar material that has evaporated just the way water will evaporate from a pan of hot water, except in this case the evaporation is at the surface of the sun, which is at about 10,000 degrees Fahrenheit. So hydrogen, being the lightest of all elements, evaporates most easily, and there is a solar wind. It's called a wind because the atoms are moving out from the sun at high speed, and they pass each of the planets in turn, and we call that the solar wind, and it has an effect on our upper atmosphere.
So we're talking about a wind or a stream of hydrogen atoms that's traveling at high speed 93 million miles and reaching this planet.
Yes, and it goes on indefinitely out into interstellar space. It's not limited just to the region of the Earth or the planets.
But these atoms don't penetrate the atmosphere. Is that the idea?
Well, penetrate might be a misleading term. They do collide with the atoms and molecules of the Earth's upper atmosphere, and they cause such things as the aurora.
Really? Now, are these atoms known by other names, or I've never heard of this before. Is this what is also referred to as some other kind of waves or rays or something that reaching the Earth, or?
No, it's just simply literally a wind.
A solar wind of hydrogen.
Well, it's solar material, which is mostly hydrogen, but not exclusively. It's about 10% helium and then other elements, but those other elements do not evaporate from the sun as easily as hydrogen does because they're heavier and they are not moving as fast as the hydrogen and helium atoms.
But like, for instance, if you were in outer space, if you were in a spacecraft and this solar wind were to pass you, would you be able to detect it somehow? Would you feel it, or would it have an effect?
It constitutes a hazard for space travelers or for astronauts, and in fact they have to take precautions to be sure that they are not in the way of an explosion on the sun, which would raise the amount of the wind considerably and constitute a hazard to their health.
Now, just how fast is this wind traveling? I mean, is it something that when it happens one day on the surface of the sun, it passes you in the vicinity of the sun or the earth a few days later, or how do they calculate that?
Yes, there is a delay, of course. It depends literally on what the origin on the sun is. There are explosions on the surface of the sun which provide more rapid particles, atoms and molecules than ordinary, but it's a steady stream for the most part, and astronauts have to be protected from that.
Now, it's not in the form of a gas, then, is it? It's on an atomic level?
Well, a gas is a collection of atoms, yes.
But in other words, it's not a concentration of atoms. It's more like an invisible stream of particles rather than in other words, you wouldn't see a gas passing you if you could
No,
see it.
it's low density sort of thing, and relatively high speed. That is, it's hundreds or thousands of miles per second. And it wouldn't be anything you could see, but it would register on instruments.
As a passing
yes.
energy? Would it cause a Gauss meter to show a reading or something, or?
Well, it might cause an electrometer to register the charges, because most of them are electrically charged. They're ions rather than complete atoms or molecules, although there are some of both.
Very interesting. And no attempt to harvest this has ever been contemplated?
Well, what would you do with it? I mean, you say harvested, that means you're going to collect it somehow, and what are you going to do with it?
Well, I know that space vessels have used solar panels or continue to use solar panels and whatnot.
Oh, well, the solar panels don't depend upon particles. They depend upon radiation. They convert radiation into electrical impulses, not particles themselves.
Well, that's really quite an interesting line of discussion right there. When I went to the Smithsonian Space Museum a few months ago, a university had donated I'm not going to call it like a microscope. It was a tube, about a 2 to 3 inch diameter tube that you look down in, and you can see what looks like meteors passing. And they say this is
little flashes.
Yeah, and they say this is the constant bombardment of what would we call this energy? I can't remember whether it's
cosmic rays.
Yeah, cosmic rays, exactly.
Yes.
And they say it's packets of energy.
Well, cosmic rays are particles, actually, and of course when they collide with particles of air, they may produce flashes of light.
Okay, it was quite fascinating to me that this kind of bombardment takes place constantly. It's not like solar radiation that we can harness, during the daylight hours, and during certain seasons especially. But
their cosmic rays are permanent and bombard the Earth 24 hours a day. They come from outer space, and they were a mystery for many, many years, but now we know at least that they come from vast distances, and they are particles, but they're not completely understood yet.
Do you think that a better understanding of them could result in our being able to harness what they have to offer in the way of energy?
Well, of course, it's hard to make predictions about things that you don't really understand, but I suppose that's a possibility, though I'm not sure that the total amount of energy is going to make it worthwhile. It'd probably be very small compared to other sources of energy like radioactive materials.
Very interesting. Now, speaking of radiation, there was something very interesting that you have recognized and that your colleagues in general have not paid much attention to. And this has to do with what we would refer to as gravitational radiation. Is that correct?
Oh, yes. Well, that is a matter that is of great interest to cosmologists, and the first proof of it came about 30 or so years ago. It was predicted back in the 1930s and 40s that there should be such a thing. You know, when electrically charged particles are accelerated, they give off radiation. So Einstein said, well, when non-electrical charges, just simply masses, are accelerated by gravity, they should also give off radiation, which is called gravitational radiation, to distinguish it from electromagnetic radiation. But gravitational radiation is so very, very weak that it was impossible at that time to detect it. But about 30 years ago, it was detected in a binary star system because the radiation carries off energy, and when energy is subtracted from a pair of mutually revolving stars, the stars will tend closer to each other, and the period of their revolution, mutual revolution, will become shorter. Well, that was in fact observed in a particular star, some 30 or so years ago, and gave proof of the fact that there is such a thing as gravitational radiation.
Although this is not generally accepted.
Oh yes, it's now considered to be an established fact, yes.
Okay, so what was the discrepancy between textbook explanations for, I think you were using an example of when a person, I mean in layman's terms, I guess you were helping me to understand how this applies. If you're looking at a star that is beside the sun, I guess in an eclipse, is that it?
Oh yes, that's the refraction, gravitational refraction as it's called. A beam of light passing close to the edge of the sun will be bent toward the sun just as a planet would be bent toward the sun. And that's called gravitational refraction. And the bending results in the stars appearing to be farther away from the center of the sun than normal. And this was first observed in nature back in 1918 in a famous eclipse experiment, which established the validity of general relativity and was really a spectacular result. It has since been observed again and again, and most recently it's been observed by the European Space Probe, not just very close to the sun, but to a distance of as much as 90 degrees from the sun.
Very interesting. And so the teaching of general relativity is accompanied by a teaching of special relativity.
Well, special relativity preceded, the theory of special relativity preceded the theory of general relativity.
Okay, for the sake of those who don't know anything about either, why don't we, in layman's terms, define what is general relativity and what is special relativity?
Okay. Special relativity is a theory which applies to electromagnetic phenomena, that is, light, electricity, magnetism, and it was developed in the latter part of the 19th century and has been developing in various ways ever since. But it seemed to be unable to accommodate a theory of gravitation as well as electromagnetism, and therefore Einstein proposed a different, a modified theory, which was called general as opposed to special relativity. And it was Einstein's general relativity that predicted the bending of light near the sun, and was confirmed by that famous eclipse observation, and confirmed even later in the 20th century by the observation of the loss of energy by a binary star, in which gravitational radiation carried off part of its orbital energy and made the two stars come closer together. So historically, special relativity was established first at the end of the 19th and early 20th centuries.
And not by Einstein.
Not by Einstein, although he did make contributions to it, as, for example, the mass-energy relation E equals mc squared. But primarily it was the work of others, German and Dutch and English physicists. But his contribution was to formulate a theory which also accommodated things like the bending of light at the limb of the sun. And it was assumed, in fact it was positively asserted, that special relativity could not match that success. But I think that is incorrect, and the work I have done, I think, shows that it is possible for special relativity to be formulated in such a way that it successfully accounts for everything that general relativity does, and perhaps for a few more things as well.
Okay, and that's where you're at odds with some of your colleagues who do not accept that as being the case.
Well, I don't know whether they accept it or not, because very few of them have made any comments to me about it.
So perhaps that's what I had understood, is that there's not enough interest in this subject for there to be even a discussion of it.
Yeah, I'll have to confess that when I started working on this, I was a little bit anxious that somebody else would beat me to it. But I discovered early on that no one is even trying, and so I'm sort of a lone voice in the wilderness at the moment.
Well, and I think that applies to a lot of the research that's being done, especially with regard to the world's energy crisis, if you want to call it that there are many people who are working out of their homes, out of their basements, their garages, or their kitchen tables even, and they're coming up with answers to mankind's energy plight, and these are not things that are forthcoming from the universities.
Well, when some of these ideas are put forward somewhere, someone in some university will probably try to test it
and confirm it.
If it's obviously no good, well, they just don't even try. But if it has any experimental evidence in its favor, then of course they will try to verify that and see if indeed it is worthwhile.
But what's interesting is that that very process that you just mentioned can indicate that it doesn't originate in the universities. It originates somewhere else, and then they end up confirming it. The greatest research has not necessarily come from these institutions of higher learning.
For example, cold fusion was investigated at the University of Utah, I believe. So some of these things are put to the test in universities, but if they are somewhat remote from orthodox theory, they are frequently passed over, and it's only some more venturesome souls who look into it.
Yeah, and that's the kind of people that we've had as guests on this program, those more venturesome souls. And you're one of them, because you've attempted to introduce a better understanding of what happens out there in the cosmos, and hopefully your keener understanding of how special relativity applies to these phenomena.
This is what I hope you're correct. I have been interested in the subject of cosmology since I was in high school, I guess.
And by the way, where was that? Where were you from?
I grew up in Springfield, Illinois.
Okay. And so you attended
I went to the University of Chicago.
Okay.
And
that's where you met your wife also. She was a student of the same subject, wasn't she?
That's right. We met at the Yerkes Observatory in Williams Bay, Wisconsin. In fact, I got started on my most recent work from a suggestion made to me by my thesis advisor, and I never did any follow-up on that suggestion until after my retirement.
Isn't that interesting?
And then I developed it and added it to a book that I had written on the mathematical subject of tensors. So the entire theory of the universe that I worked out on the basis of previous work done by an English astronomer named E.A. Milne resulted from that suggestion.
Now, when you say a theory of the universe, you're referring to a theory of everything, or?
Yes and no. When you say theory of everything, that would imply that there's a connection between quantum mechanics, or theory of atoms and fundamental particles, and the universe, which undoubtedly there must be, even though we don't know what it is for sure. But a theory of what the universe is and how it behaves. Back in the 1920s, an astronomer at Mount Wilson and Mount Palomar named Edwin Hubble, whom most people have heard of by now,
sure,
began to study what were then called the spiral nebulae. We now call them galaxies. Our Milky Way is a galaxy, and there are hundreds of billions of galaxies in the sky, visible only, for the most part, only with the very great telescopes, the big ones, most of which are very new. But at any rate, what Hubble discovered was very interesting. He found that galaxies are going away from us. They are receding. And not just in any fashion at all, but the farther away they are from us, the faster they're receding. And that is known as Hubble's law. Well, Hubble's law was never questioned until recently, when some astronomers particularly a group out in California, measured the distance and velocity of some of the very faintest and most remote galaxies they could find. And they discovered what they said was that those galaxies were farther away than Hubble would have expected. And the reason why they were farther away was they were fainter than they should have been, according to Hubble's theory. Well, that's a possibility, but there's another possibility, and that is that they are fainter because they are receding at very high speed. In fact, the velocity of recession, the greatest velocity of recession so far measured on any galaxy is about 180,000 miles a second. Well, that's just a few thousand miles under the speed of light. So that's an enormous velocity of recession, and no material body can go as fast as light. So this is really a remarkable observation. And these astronomers said, well, why is they asked themselves, why are these remote galaxies as faint as they are? We didn't think they were going to be that faint. Why are they that faint? And the answer they gave themselves was, they're farther out than we thought they were. Well, I think my answer would have been, they're fainter for some other reason than distance. And of course, obviously, something farther away is going to be fainter than it would have been closer up. So my explanation is that it's not because they're farther away, it's because of something called attenuation. In other words, the beam of light which they are sending us has been stretched out because each second the light has farther and farther to go, significantly farther to go. I mean, if this object is going 180,000 miles a second away from us, then each second the light has to travel that additional 180,000, and it doesn't get here at the end of a second. So if it doesn't get here, the object is going to appear fainter than it would have. And that is the explanation rather than greater distance.
Very interesting.
Did I explain that in a way that anybody can understand?
Yeah, I think so. And if not, they can click on the rewind button and hear it. And keep hearing it until they understand it. But I think you made it pretty clear. It's very fascinating. Unfortunately, we've come to the end of our half hour, or exceeded it.
Really?
Already? And so perhaps we can get back together and discuss in greater detail other aspects of this fascinating subject. I'm sure there are plenty of other things that will come to mind that I can make note of, and then you can too. We can discuss them the next time. But I thank you for joining us. It's been very interesting, and perhaps in the near future we'll be able to repeat another program where we delve deeper into some of these things.
It's been my pleasure. Thank you for inviting me.
And thank everyone for, thank you to all who've paid attention to this message. Thank you very much, and good night.